Welcome to The Explainer. Today we're diving into this completely awe-inspiring intersection of cutting-edge tech and human biology. We're looking at a space where the futuristic promises of additive manufacturing are quite literally colliding with the everyday life-or-death needs of healthcare. We're talking about 3D printed anatomy. Okay, let's just jump right in, because the real-world applications are already happening as we speak. Picture this. A severe trauma patient comes in, someone who's suffered catastrophic bone loss, maybe from a bad accident or a gunshot wound. Over at the Gulhane Medical Design Center in Ankara, Turkey, doctors and engineers aren't just patching these folks up with your standard run-of-the-mill generic plates. No, they're literally using 3D printers to create entirely custom skulls and bone replacements. It's tailored perfectly to that one specific patient's anatomy. It is a completely customized medical miracle. But, this brings us to a fascinating question, and it's really the core of what we're unpacking today. How exactly did 3D printing, something that for years most of us just viewed as a neat way to print little plastic trinkets on our desks, evolve into a literal lifeline for critical trauma patients? How do you go from printing plastic toys to printing human bones? To answer that, let's look at the massive systemic shift happening across global healthcare. Here's our roadmap for today. 1. The custom body part. 2. Hospitals adopt 3D printing. 3. The billion-dollar boom. 4. Heavyweights and market drivers. And finally, 5. The future of bioprinting. Section 1. The custom body part, from desktop plastics to human implants. So when we talk about 3D printed medical devices, we kind of need to redefine what we think we know. We aren't just talking about a simple cast or an external brace here. We are defining artificial devices that completely replace missing biological structures. They're built up layer by layer right from a digital 3D model. And the materials, absolutely crucial. We've moved way, way beyond basic plastics. Today, we're using advanced biomaterial inks, plus medical-grade metals and alloys that can actually integrate fully with the human body.
Section 2. Hospitals adopt 3D printing, moving the lab to the point of care.
So, how does this actually play out for a real patient? Well, let's walk through the workflow. It all starts with advanced medical imaging. Think high-res CT scans. Facilities like the one in Ankara use this incredibly precise 5-angle optical scanning to capture the exact defect. Next, they take that data and build a flawless 3D computer model. Then, they actually print the custom implant. And that leads to the ultimate goal. Because the implant fits perfectly, surgery times are drastically reduced, and shorter surgeries mean a significantly faster, smoother recovery for the patient. And here is the number that really proves why this matters. 30%. Research is showing that using these 3D printed models and patient-specific guides gives surgeons a massive 30% improvement in accuracy. I mean, when you're dealing with incredibly complex orthopedic, spinal, or cranial surgeries, a 30% leap in precision, that's a total paradigm shift. Because of results like that, hospital adoption is just exploding. Get this. Over 65% of hospitals in developed economies are currently looking into or already setting up their own in-house 3D printing labs. They literally want this technology down the hall from the operating room. We're seeing major global collaborations pushing this forward too. You've got the joint R&D lab between Singapore General Hospital and Nanyang Technological University, or the clinical tie-ups between UNIST and Pusan National University Hospital in South Korea. The research is happening right there, directly at the point of care. Section 3. The billion-dollar boom, scaling the medical miracle. Now let's zoom out a bit to the macroeconomic side of things, because this clinical adoption is scaling incredibly fast. Right now, in our 2024 and 2025 base years, the market sits somewhere around $2.6 to $4.4 billion. But check out that trajectory. By 2030, forecasts are putting it at nearly $9 billion. And by 2034, we're staring down a staggering valuation of up to $20 billion. That is an explosive compound annual growth rate of roughly 16 to 18%. Just massive. To really wrap our heads around a boom like that, we need to see exactly where those billions are flowing. The investments are heavily segmented. Under type, the money is pouring into custom implants, prosthetics, surgical instruments, and the super advanced field of tissue engineering. The raw materials driving this: specialized plastics, biomaterial inks, and advanced metals. And the applications getting the most funding right now are orthopedics, dental, spinal, and cardiovascular. Section 4. Heavyweights and market drivers. The money and the movers. First off, just look at the venture capital flying into this space. $52 million. That's what Zeta, a California-based nanotech and 3D manufacturing company, pulled in during a recent Series B funding round.
That single number really highlights the massive influx of private capital from investors who are just incredibly eager to scale these capabilities globally.
But hey, it's not just the startups. The established corporate heavyweights are absolutely dominating and consolidating this space. We're talking major players like 3D Systems Corporation, Materialize, EOS, and Renishaw. And they are making aggressive moves. Stratasys, for example, recently bought up Covestra's additive manufacturing business for 43 million euros, specifically to broaden its materials portfolio. These big players are arming themselves for a true manufacturing revolution.
So what's actually driving their sales? Well, a couple of major medical demands. First up, cardiovascular disease. There is a soaring need right now to print patient-specific cardiac models from MRI scans. Surgeons use them to literally practice a complex heart surgery before ever making an incision. On the flip side, we have rapid dental innovations. There's a company called Proclaim that just launched a custom 3D printed mouthpiece proven to wipe out harmful gum bacteria in just 7 seconds. 7 seconds. Honestly, that's about how long it takes me just to find the dental floss. That is the power of a perfectly customized fit.
Section 5. The future of bioprinting. Engineering human tissue. Okay, this is where we leave the rigid metals and plastics behind and step into a truly mind-bending frontier. The R&D happening right now around engineering living human tissue is absolutely breathtaking. You've got the EU-funded Polina project working on bioprinting structures that perfectly imitate natural tissues. Stratasys partnered up with CollPlant to develop regenerative breast implants, implants that actually modify the body's immune response to help regenerate natural tissue. And over at MIT, they're printing flexible robotic heart replicas. Seriously, the research is staggering. Listen to this. MIT engineers are developing customized treatments for patient-specific heart forms and functions, a procedure to 3D print a soft and flexible replica of a patient's heart. Think about that for a second. Using polymer-based inks, they are literally printing soft, flexible shells in the exact shape of a patient's own heart and aorta. And they can control it to mimic that specific patient's blood pumping ability. It's an exact beating replica. Which leaves us with this final, pretty wild thought. We started this explainer looking at rigid 3D printed plastic and bone. But if engineers can 3D print a customized beating robotic heart today, what living, breathing organ are we going to be printing tomorrow? The trajectory of 3D bioprinting isn't just changing healthcare. It's completely redefining the limits of human biology itself. Thanks so much for joining me for this explainer, and definitely keep your eyes on this space, because the future is quite literally being printed as we speak.